Okay, so volumes of revolution. So this is connected to what we've been looking at. So you can see here that we're going to focus on this area here between the values of B and A. And what happens is that we would be asked to imagine that that portion of the graph is rotated around the x-axis. Okay? So it's going to go through 360 degrees, or we consider it as 2 pi, okay? Because we know that 2 pi is also 360. Hence, forthwith, I have my models. So let's imagine that this is my function. This is my x-axis. What happens when I rotate it around the x-axis? Oh, wow. It becomes a solid. What do you not get?
Yeah, wait a moment, Tony.
That's kind of pretty.
I think we more choices. Here's my little bit of graph.
Okay.
Here's my x-axis. I'm taking this line and rotating it around the x-axis.
Okay.
So it's going all the way around. And it forms a solid.
Okay.
Are we excited about this?
Yeah.
Good
Yeah.
show and tell?
Yes.
Do you understand it? Because this picture, not so good.
No.
This, lovely. So, what we're going to do is we're going to find the volume of this. Okay, so we know that, we can find the area of this, yes, by finding the integral. So if we want to find the volume of it, we're actually going to use this equation, this formula. So we'd have between B and A, we would have pi, what we call this, y or fx? I'm going to put y. So what we would do is we would square the function and we would multiply it by pi. Now there's a big long but there's a big long explanation as to why that happens. It's, as I say, it's connected to the fact that it's area and volume. I wouldn't normally do this, but we're kind of running a bit behind time, so I'd rather not go through it if we're happy just to use this formula. Are we all happy to use it?
Are we given that?
You're given that, yeah.
Cool.
Okay. Now, something that people often forget is squaring. Okay, so we need to make sure you always square your function. And sometimes people will forget the pi. Now, this pi can sit out the front here. Okay? Because we know that constant values don't have any effect on integrals anyway. So if we stick the pi at the front, that's probably a little bit easier. We could integrate, square it, integrate it, find a value, and then just have pi as our answer. Now, this could be on paper 1. So if it is on paper 1, then obviously you're not expected to know the exact value, you'll keep it in terms of, okay? All right, yeah. If it's on, but most of them, to be honest, are on the calc paper, and we just learnt yesterday, remember, how to use the calc to do these integrals. So it's, so you would just write the function in brackets and put a squared outside it. Okay, so the function that they've given you, pop the squared in.
And you would put the pi where?
You could, so do the integral, and then multiply by pi at the very end. Okay, crispy ants? So here's an example. So the curve y is x cubed is rotated through 2 pi about the x-axis. So your question will always start talking about things like that. The solid created with the boundaries between x's 2 and x's 3 would be as shown. Okay, so the volume of this solid, we would use the following formula. So we've got integral between 3 and 2. Let's keep our pi to the front. We've got x cubed, and we are squaring that. Okay, so we're using that formula. The limits, we've got our function's being squared, and multiplied by pi. Presbyans. So what's x cubed squared? What do we do with our numbers?
6.
Multiply. 6. Yeah. I know lots of people said 6 is 2, you said quite quickly 9. So making sure she's comfortable that it's 6. Yes? Okay, so we've got now this. So my pi stays here, open my square bracket. So integrate that becomes x7 over 7, yeah? 3, 2. 3 to the 7 over 7, take away 2 to the 7 over 7. Or let's not do that in our heads, that's way too hard.
I agree.
So let's just chuck that bad boy in the calc. Does anyone have one?
Now let's see if I do this right.
Yeah, you're the only one doing it as well, so we haven't even got a checker.
Look up
Come
there.
on, Leo.
Alex is not comfortable with this situation. She can see the terror in Manly's eyes.
Sweat dripping down my eyebrow.
The pressure is on. But notice none of your friends in this area are rushing to like assist you.
Leo. I have confidence in you. I'm going to get my answer.
Not.
Did you do this bit or multiply by the pi also?
I did all of it.
Roger that.
So 924.27.
That sounds right to me.
I know it's right.
Uh-oh. So what would we always put on things to? So what's that 3 sig fig?
924.
0.1.
3 sig fig.
Yeah.
What do you mean young? 1 0?
Yeah. She said. 3 sig figs.
Yes, yeah. What she said.
Is that right?
What she said.
I think it's right.
Do we have a confirmation? Oh, no, we really don't.
She wrote it in.
I don't know.
She did?
Oh. You probably did it.
I'm sure I did, Maddie. 3 to the 7 over 7 minus 2 to 7 over 7.
What are you looking for?
And a pi in the front.
Oh,
you do the pi. Roger. Alright, okay, so that's good. Let's rock and roll. Do we get that now? See, Maddie? All good. You know. So a semicircular area is created between the curve and the x-axis. The curve is then rotated about the x-axis to create a solid sphere. We're going to do that during the lesson. That's abundant.
It's only
Let's hope they're not. Let's hope they're not running it.
Yeah, that's good.
Do you have a backup plan? Does someone want to grab your stuff if they?
We will.
Grab your stuff.
There we go. Alright, so what are we going to do for this bad boy? So this is our function.
Yeah.
We're rotating it around the x-axis to create a solid sphere. So what would our volume be?
Pi, squiggle, 3 integral minus 3. And then what you do, you have the bracket, the square root of 9 minus x squared. And then you square it, and then you dx it.
Trace the ants. Okay? So make sure that you write that statement. Okay? Because if you've got that statement, you're at least going to get something, even if everything else goes pear-shaped. Okay?
Would you do that to the power of a half?
Now, here we go. We've got a square root, and we're squaring it. So what happens? They cancel each other off, yes? So now we've got the integral between 3 and -3 of just 9 minus x squared. You all happy with that?
Yeah. I'm saying to Miss Harrison, if back to if this was in calculator,
Yeah?
it wouldn't matter if we just put all of them because it would-
Correct. As long as you've written this, you're good to go.
Okay.
And in fact, the thing is, it's frustrating quite often because these kinds of questions are often on the calc paper and they're really obscure functions, and students look at them and go, oh my goodness, I'm never going to be able to integrate this, and it's going to take me ages, and it's worth like 2 marks.
Yeah.
And it's because they forget that they're supposed to just chuck it in the calculator. So if you see it on the paper too, just chuck it in the calculator. Make the statement and then put it in. Okay, so this bad boy, so we've got pi, square bracket, so 9 becomes,
9x
yeah,
minus x cubed over 3.
yeah, and then hang our limits.
Minus 3. So then it's 9 bracket 3 minus 3 cubed over 3. That's going to bracket minus 9 bracket minus 3 minus 3 cubed over 3.
Oh, she's on a roll. Okay, so we need to chuck that in the calc and get an answer by the 40. Oh, Mally, you are on fire with your calculator work.
I actually write this in my report.
In January.
She knows how to use a calculator. Yeah.
I said to your mum, you participate really well in class. I did. Right, okay. So obviously, it's not always going to be quite as straightforward as that. I haven't got one of these to show you, unfortunately.
Oh man.
But sometimes they're going to just want to rotate a portion of things around here. So obviously, when that's rotated, it's going to have a hole in the middle. So if this was more of an ellipse, we would have like a donut hole. Yes? You get that? So when that, see, I haven't got any models, so you don't really know what I'm talking
So
about.
it's like this.
So when I'm rotating that, it's just gonna, this is gonna be a gap in between.
So it's like
Wait,
Yeah.
what?
like a donut.
Just like a donut hole. Like a ring donut.
So which part is the
So
shaded
this
region?
bit is gonna be rotated. And then this is gonna be your gap in the middle. We'll double this.
Okay.
Yes? No?
Little fish.
No fishing bowl. If we're going to do that, then we're going to square our top function, subtract our bottom function squared. Okay, so we're going to square our top one, subtract our bottom function squared, and multiply by pi. So yeah, really, really similar. So all you just have to remember is that you're squaring stuff. Now, I don't think you get given this formula. Someone may want to check. So you all have your formula booklets, I'm sure. But I don't think you get given that one. So you just have to remember that you square them both rather than subtract them and then square it. Okay? This is a worked example, so you don't have to write anything. But I thought it's just good to have something. So we've got y equals x squared plus 6, y equals x minus x squared. So we've got a little diagram there to see which one is on the top. Okay, now they've asked to show that. So remember for show that questions, it's actually quite nice because you get to do what you would normally do, but you know what the answer is supposed to be. So you're going to come out of that knowing that it's right. It also means that you're not going to stop yourself from doing any other mark, because they've then said evaluate this. So obviously we know to evaluate it, we would then substitute the numbers in. So if we've got this wrong, we have potential of losing marks for this, but because they've shown us it, we're good to go.
And it's not in the formula booklet.
It's not? Okay, thanks, Katie. So you do need to make sure you remember this bit. So if you've got two functions, you square them individually and subtract one from the other, okay? I have to say, it's one thing that I always have to double check myself, because sometimes I think we just subtract them and then square it. No, you square them and subtract them, okay?
You have to identify which one's F and which one's G.
Yeah, so you always need to know which one would be on the top. So again, well not again, this one here, what kind of function is this?
Positive.
It's a positively happy one. This one is a negatively sad, so this one's going to be the one on the top, okay? So you need some kind of knowledge about the functions to decide which one's top or bottom, okay? So then we've got to find where they meet, okay, because that's always important. So there we go, we've equated them, lovely jubbly, and we found it's 1 and 3. We've then got our volume of revolution, so they put the pi at the front, they put that second function first and squaring it, subtract the other one squared. Remember when you're squaring things like this, write the two brackets.
Foil.
Because you need to use FOIL, yes. Okay? So you've got then, this is your expansion for that one, this is your expansion for that one, subtract one from the other. Now, obviously this doesn't look exactly the same as what we've been asked to show that it's equal to, but ideally you're spotting that they had a 4 at the front. So if we divide all of these numbers here by 4, we end up with what they had. Okay? So as I say, show that questions are nice because you get to the end of it and go, I've done it. But for show that questions, you need to just go through the process as you would do normally and then double check to see what they give you. Okay?
Wait, so why do we divide by 4?
Because
they had a 4 at the front.
So you just divided all the answers.
Because you had to show that it was equal to this.
Got you.
So whilst up to this point here is probably what you would have done in the exam yourself. The fact that they've got a 4 there, you just need to, and to be honest, if you've got to this point, just write what they had and hope that your numbers match, okay? So kind of fudge it in the very final step and hope that yours are good.
It's like ever gonna be like a time in this where it did
Where it doesn't match?
Where it don't.
where it did where like it doesn't equal add up or like, you know what I'm saying?
Yeah, if you've made a mistake. And that's
So it has
yeah, so that's where, and that's what
That's kind of
I
the
can't
point.
stress enough because we show that questions, it's really nice because you go through it and you're like, yes, I have got it right. Or if you haven't got what they've got, don't just fudge it. Like try and make sure that these numbers are all divisible by 4 and therefore you've got the same answer. But if it's completely different, you need to go back and have a look at your working because something has gone wrong. Okay? I mean, that's, for this one especially, finding the 2 intersecting points should help you because they've told you that it's 3 and 1. So that should help with this kind of process here. And then obviously they just chucked it in the calc and got 184. Okay. What have I got here? Just one more example, I think. Alright, so yeah, the area enclosed between the curve, the blur, and the line of blur is rotated through 2 pi radians about the x-axis. Find the volume of the solid generated. So this is the kind of vocab that you'd be seeing in questions like this. So first we need to find the points of intersection. So we would write
4 and 2.
or secretly, no.
They don't intersect them.
So how do we find them?
You
How do we
equate
find
them.
You make them equal.
Yeah, I mean it does say it just under here, but that's okay. Okay, so we would write that.
That's funny.
Okay, so we've got this here, and we're going to equate it to 0. And so we've got 4 on both sides. We've got 0 equals x squared minus 2x. Yeah. I'm kind of squishing it all in. We shouldn't. So I'd say that 0 equals x squared minus 2x. So bring the x out, we get x minus 2, which means x is 0 or positive 2. Okay, so there's our 2 values. I said that just here anyway. And be careful with their value from the diagram. If you're looking at the diagram, remember we're always looking at x values. So this one happens when x is 0.
I keep that afterwards.
Okay. So hopefully you're comfortable with the fact that that first function, the 4 minus x squared, excuse me, that's the negatively sad, so that's going to be the one that's on top. So we've got the integral between 2 and 0, we've got our pi at the front, we've got 4 minus x squared, oops, 4 minus x squared, subtract 4 minus 2x squared dx. So as before, you need to just make sure you've got that statement. And then to be honest, you can just chuck that in your calc. I'm comfortable to get you to practice doing that. So you would just literally type it in as is. Check to see, obviously, if it's on the non-calc paper, you also need the calc, but you don't use the calc. You can't use the calc, but most of
And you
these.
said we can do it afterwards, right? Multiply by pi after.
Yeah. Or you can just put a pi in the front, you should be able to. Alright, okay, so we're totes. Everyone's managed, she's had a storming cat.
So you didn't get that.
I didn't get that.
Oh, shush now.
Well, I did it right, so I don't know what you did wrong.
I did it twice, so. Oh,
What did Leah get?
20.1.
Huh?
20.1.
Oh. Alright, okay. So it's one of those. So,
Maybe let's try it again.
I'll double check, and we can talk about that.
Mom.
Alright, so it's been decided that Mally had a little bit of a do there, so it's this bad boy. Okay? I don't know what I'm still talking about. And it does make more sense, to be fair. Right, so calculus and kinematics.
You don't have that for me.
I just brought it round to you.
Oh, boy.
So this stuff is actually stuff you did cover at GCSE, and it may seem like 100 years ago, and you may not recall, but I'm hoping that it might start bringing back some memories. So calculus and kinematics is very much connected because we are often, or we may well be given an expression for displacement. Now, if you do physics, you've probably heard of all this stuff already. So displacement would be given or assigned the letter S. Velocity, which is speed, would be V. And the connection between displacement and velocity is that if we differentiate our expression for displacement, we get an expression for velocity. Okay? If we differentiate our expression for velocity, we end up with acceleration. So A is dv dt, or in other words, the second derivative for S.
Never mind, you answered.
Okay? So this, remember, stands for second derivative. So if we were given this and asked to find acceleration, we would just differentiate it twice.
So it's displacement or distance?
Yes, it's just a fancy pants distance. All of our expressions for kinematics are in relation to the variable t. Okay, so it would be S equals something to do with t, where t is time. Okay. Well, obviously, if you can differentiate something to get from one to another, we now know that we could integrate those expressions to get from one to another. So we may be given an expression for acceleration and asked about the velocity, so we would know to integrate it. Okay, and similarly, displacement would be the integral of velocity. So it's just a straightforward from one to another. Okay, it might say something like, here's an expression for the displacement. What's the velocity when t is 5? So you would differentiate it, substitute the value of 5 into that expression. Okay, and most questions are pretty straightforward. One thing I've just put here is that don't forget that if you're integrating something, they need to have given you some other extra information to enable you to find C. Okay? So if you've integrated, so if they've given you an expression for acceleration or velocity and asked you to find the velocity or displacement, they would have given you some additional information to allow you to find C. Okay? And the final thing, and it does come up quite a lot, is talking about total distance travelled. So the total distance that you've travelled would be the integral of the velocity. Now notice this has the modulus sign. So this is where, when we were looking at integrals above and below the x-axis, it's important that you are considering those kinds of things when it comes to distance travelled. That's pretty much all I'm going to talk about kinematics. I have got some past paper questions just on kinematics questions, so I can hand those to you as well, but it's just more of an application of calculus that comes up quite regularly. Okay, it could well be that you're just going to have a straightforward, no mention of kinematics whatsoever, but or they could chuck one in. Okay, so it's just a kind of a side part. Right with that?